can begin this discussion section. Do we have both the leaders for the discussion session online? Yeah, perfect. All right, you can start, I think.
Yeah. So, okay, I will start actually, and then I will give the floor to James. So we have prepared a few slides about these discussions about the jet launching mechanism. So first of all, as you know, and I think that James shared the same thing, is that we are not expert at all about jet launching mechanisms. Anyway, we have some background on modeling and observations, of course, and we have some questions that rise from what we have seen during this meeting. So, of course, again, there are apparently two main jet flavors that we use to explain jets. So, Blandford-Snijek, Blandford and Payne. The point here is that I think it's progressing, but there is, I mean, these processes are actually very complex, and the way theoreticians can give informations to observer is quite complicated because the models are complicated. A few examples, for example, the Blandford and Snijek models is known since '77, and I think that the most recent simulations with peak simulations that show the way you can load the Blandford-Snijek model with matter has been done only very recently in 2020 by Benjamin Crinquant and so on with peak simulations. And very recently, there was a strong debate about the effect of these Blandford-Snijek processes by the paper of King and Pringle in 2021, and very rapidly discussions with Komissarov saying that actually the work by King and Pringle was not completely correct, meaning that actually people expert on that have already a lot of discussions about that. So clearly the link with observations is certainly even more difficult to have. So we have to strongly work with theoreticians to try to understand signatures that we may have between Blandford-Snijek and observations. The same for Blandford and Payne. I guess that with Blandford and Payne, it may be easier. The point is that, and it was clearly explained in the talk by Jonathan, is that in this case, clearly everything happens in the accretion disk. I mean, at the surface of the accretion disk. So clearly, you need to understand this transition between the accretion disk and the jet to understand what happens in the Blandford and Payne jets that you produce and how you can relate this with observations. So my point here, and of course, I cite only a very few number of papers, but there's a lot. My point here is that, again, the link between theoreticians and observer should be done, but it can take some time, actually. I think that one result from Blandford and Payne type of simulations, which seems now to diffuse in the community, is that the accretion velocity can be quite large, and it has strong effect on the accretion disk. And so this is something that I guess at least more, people working on models of corona, for example, or accretion disk can take easily into account. Even if they do not control completely the Blandford and Payne type of model. The second point, it was already raised by Jonathan, and actually I took a picture from the talk of Samuel Barnier, was about the presence of this large-scale magnetic field, which seems to be needed if you want to have one of the two processes, Blandford-Snijek or Blandford and Payne, or both together. And here in this sketch, the point is that perhaps to explain the evolutions of the radio emissions can be due to an evolution of the distributions of the large-scale magnetic field. But of course, the point is how this magnetic field is evolving with the accretion rate, for example. And this appears to be a crucial question to understand the evolutions of these accretion ejection flows and the jet processes. So this was the views from the, let's say, modeling and theoretical point of view. And I give the floor to James for the observations point of view.
Thank you very much. So having reviewed some of the theoretical mechanisms that we think are likely of most interest here, I wanted to just throw out the questions about what's the best way that the observational community can go about probing jet launching in X-ray binaries. And there are a number of advantages that we have over looking at more massive black holes, multi-wavelength observations and time resolution being some of the key ones. So some obvious signatures that have been suggested over recent years. So detailed, intensive multi-wavelength campaigns have thrown up some interesting hints. Things like the optical fast timing signatures that Poshak and his collaborators found looking at V404 Cygni, as shown on the left here, were very suggestive of something going on down at the jet base that we might be able to pick up immediately before the launch of a radio flare. We've heard a little bit already this week about tracking jet ejection events with VLBI, in particular a paper by Callan Wood and collaborators looking at really tracing the ballistic motions of the ejector back in time to see what was going on in the accretion flow at the time of jet launching, and what can that actually tell us about what's causing the jet launching and potentially what the mechanism is. And then obviously the third powerful comparison is looking at different classes of compact objects with a range of different parameters. So whether that's looking across the mass scale between black holes, neutron stars and white dwarfs, as Elmar Kerding had in this very nice paper on SS Cygni, and suggesting that there was similar behavior across these three classes of compact object. To some of the more recent work, you see here a figure from Jacob van den Einden showing radio emission from a high magnetic field, relatively slowly spinning neutron star, which was significantly weaker than seen in the bulk of the rest of the neutron star population, and certainly the black hole. So comparing different compact objects across different regions of parameter space, magnetic field strengths, spin rates, and so on can potentially tell us something as well. So if we can move on to the next slide as well. The one advantage that we really don't have in X-ray binary jets, and I think there's been some chat about this on the Slack, is that even the best resolution that we have on VLBI scales can only probe down to a few 10 to the 6 RG or something. And so if we really want to actually resolve what's going on, we have to go to the more massive nearby supermassive black holes. So the very nice recent work from the EHT showing this edge Brighton structure in SEN-A, and also suggesting that we see this collimation zone as we get down very close to the black hole, reminiscent of what is seen in M87, which of course has fantastic imaging from the EHT as well. So we can't actually probe that in the X-ray binaries. We don't have the resolution, but we can potentially take some clues, at least in the jets that are similar to the low hard state type, relatively steady jets, even if not these bright discrete ejecta that we see during outbursts. So I think on the final slide, we just put up a few questions for people to ponder in terms of both theoretical questions and how can we approach these things observationally via computation, via analysis, to try to use these stellar mass black holes where we do have advantages in timescales, in multi-wavelength coverage, to try and attack this question of how a jet's launched. So I think that's all that we wanted to say, unless Pop has anything to add. We can throw open the floor for questions.
Sorry.
I don't see anyone in the room, but Greg has had his hand up for quite a while on Zoom.
That's okay. I just had a general question for the entire audience, because we often talk about jet launching, but as James and other people have pointed out, that there are multiple types of jets. There's the compact steady jet, and then there's the transient jet ejecta. And I think a reasonable question is it the same mechanism in both cases?
Very good question. I may give some answer about that, in the sense that actually there are some approaches where people can believe that you may have two different signature due to two different type of jets. One, I mean, the one observed during the hard state, which appears to be quite stable, can be Blanford and Payne, and you may have pairs appearing and producing these strong flares during the transition, and producing perhaps these very variable radio flares. So suggestion that you may have indeed two different processes there, but I don't know if there are any signature, more clear signature of the of anything different between the two processes, actually.
I mean, we certainly think that the transient jets, the best explanation is shocks, whether internal or possibly external. In some of the models, the Ishem model that Melania was starting to talk about, and Julian Malzak and his collaborators have done a lot of work on, the emission from the hard state jets is suggested to be the superposition of shocks up and down the emitting region. That said, when we go to the EHT jets, we tend to see these very edge-brightened structures without a lot of emission in the central parts of the jets, which wouldn't seem to be consistent with the standard picture that we seem to have of shocks at various different distances downstream that are more or less across a particular, the jet axis at a particular distance. So is that telling us that our picture is wrong? I'm not sure. I'd be interested to hear some perspectives from some of the theoreticians or the people that are working on the AGN and what EHT is telling us. So Sarah, maybe that's a good segue to your question.
So yeah, I mean, from the EHT side, of course, the main tools we're using are GRMHD simulations. So there's all the caveats, that we've been hearing about here and there, but for sure, it looks like when you have good VLBI images, at least of AGN jets, it seems like most of the radiation is coming on the edges. And in terms of the modeling and interpretation, like Kaushik Chatterjee's been working on this and other people, but it seems like the only way we can really explain this is via more like instabilities along this boundary region between really the Blanford-Znayak jet and the Blanford-Payne winds. And that's why I think it comes back to these questions that Pop was bringing up. We need both, right? To explain what we're seeing, we can't just have one kind of jet, and the interaction between them, in fact, may be the interesting region that's a kind of got qualities of the two. But I would say the shock idea is less, I would say, less fitting in these very strong magnetic field dominated regions, and probably more like instabilities. But that doesn't mean it doesn't match with the idea that the noise and the variability can be driven, by the disk, because if these field lines are anchored in the disk, at least in part at this interface region, then if something's wobbling down there, it's going to be wobbling and helping drive those instabilities as well.
But then doesn't this mean that actually in terms of simulations that we have to put a lot of effort on hybrid simulations like the one we have seen by ILEC, where you have peak simulations and MHD simulations. If you want to follow, for example, the acceleration of particles between the Blanford-Payne and Blanford-Znayak, it seems to be necessary.
Well, it's necessary for any simulation that you want to link to radiation. You have to deal with the microphysics, and that's one of the biggest problems, right? And I think coming back to what Navin talked about, we're in the early days, right, of trying to understand, what happens at the microphysical level, also including cooling effects, and the differences between AGN and X-ray binaries can be quite huge. So there's some of the assumptions that everything scales may also break down. So yeah, there's a lot of caveats, and I think these are the things that worry me anyway.
Thanks, Sarah. That's really interesting food for thought. So, a lot of the work that's been done in this field has often been in terms of, well, this helps us to understand the supermassive black holes in AGN and the accretion there and the jets there. And if the scaling is breaking down even on these very small scales, that's obviously a little concerning in terms of trying to attack this problem from a bunch of different angles. So is that, obviously, as you get out to larger scales on the environment, things are going to break down as that's not going to scale between the objects. But if down in the inner regions where you're worried about the microphysics and the cooling, that causes the lack of scaling, it becomes a bit harder to make that progress, I suppose. Is that a concern?
Were you addressing that to me or to everybody? Sorry.
Well, since you brought it up, I'd like to hear your thoughts.
Yeah.
But I know Poshak has his hand up as well.
Sometimes I wonder if we don't get the same answers for different reasons. I mean, in the old days, we used to think about the 100 keV thermal distribution as coming from virial balance, right? And now maybe we can get the same sort of thing just from this mechanisms that are being looked at in PIC simulations, but the underlying physical reasons for the 100 keV are quite different. And that might be different between, say AGN and X-ray binaries. I mean, I think, but I think you have to separate the parts where the dynamics maybe dominate a little bit and where you have dynamical similarities. I think that for sure is going to be scaling between the X-ray binaries and the AGN. And we already know that the radiation will not scale exactly, even if you take the same properties in terms of scaled powers in terms of Eddington and size in terms of RG, the actual physical numbers you'll get for density and temperature and so on will be different. So I think in that sense, we're probably on fairly safe ground, but it's more like, I don't know if Mike Novak is here, but he used to always say this. He'd show these pictures of the black body and then look at what simulations show you what a disk is doing. And it's like, how do you get a black body out of this turbulent, mess? And so somehow we might be saved by the macroscopic averaging, but that makes it harder too to understand what's happening at the small scales. And I think that's where things like EHT and PIC simulations, it's all coming together. But indeed, the field is moving towards trying to put PIC techniques in these regions in simulations. But of course, it's such early days that there's not like a big, strong conclusion coming out of this yet about what mechanism is dominating. People think it's reconnection. Maybe there's some shear,
We have a comment from.
So there was the hand raised by Poshak, but I don't know, Andres, do you want to react on the discussions with Sarah or it's something different? So Poshak, perhaps you can, because you raised your hand since a few minutes now.
Okay, thank you. I'm happy to give the floor to Andre if you want, but fine, this is related somewhat, I guess. Hope you can hear me well. So again, I'd like to come back to the possible connection with solar physics, which wasn't mentioned today. Now, I'm not a sun worshiper. I keep bringing up the sun and I love sitting out here, as you can see, in sunny southern coast of UK. But I think it is the nearest star where we have, some possible real observational constraints on magnetic field strengths and behavior of flares, etc. And I believe some of the early MHD models were also based on like the solar wind Parker wind instability model. You can correct me if this is wrong, etc. So I'd really like to understand what that teaches us. And also the MHD models make some very specific predictions about some of the critical surfaces, which I think we heard a little bit about in the last talk. There's also the magnetosonic fast point, etc. Do we now have observational constraints which actually pin those down? Are we actually starting to constrain some of those models usefully or not? And finally, also related to this, one other observational constraint, which we've not heard about at all in this conference, I think, and surprisingly, is the RMS flux relation by Phil Utley and others. And several of us have published it in a multi-wavelength perspective as well. In principle, that can be explained by large-scale magnetic fields and interconnection between different zones. So again, is that a constraint that can potentially shed light on some of these issues?
Thanks, Poshak. Some interesting points to think about there, particularly in terms of the reconnection and what we can learn more locally. I don't know if there are others out there in the audience who want to comment on some of Poshak's points. I can't see who's in the room. Phil has his hand up, so this sounds that may be relevant. Phil?
Yeah, so no, just on the RMS flux relation, I'm not really sure with the reconnection side, because we looked at this a lot, in when we sort of were working on the interpretation of the RMS flux relation. And the problem is that there are all these models, for example, avalanches of flares, but the problem is that they have to start somewhere. And, because there's some sort of random independent events happening, right? You end up with something that doesn't look like the RMS flux relation and doesn't have the log normal flux distribution and all these things. So I'm not convinced that can work. And people have often claimed these effects in, for example, emission from the sun. but actually what they do is they're plotting something different, like the distribution of fluences or something like that, not the actual total emission. And it's also easy to get linear RMS flux relations from any kind of positively skewed flux distribution. So you have to have the log normal flux distribution plus the RMS flux relation. And that can, at the moment, as far as I know, only really be produced by propagating fluctuations where the fluctuations multiply together, the Ljubalski model. So I'm kind of not that convinced yet. And I accept that what you see in the jets is actually, you know, you do see these linear RMS flux relations there, and to some extent the flux distributions. But I wonder to what extent that's just because the accretion flow is talking to the jets. So certainly a constraint, but I think it's quite actually hard to do with anything other than propagation.
Yeah.
I might ask something really silly or naive, especially to the last speaker, that you worry about all these velocities.
Can you speak in the microphone?
And accelerations. Oh. Yeah, so maybe naive or silly question, especially to the last speaker and everybody who worry about the velocity and the acceleration. That I'm wondering, like in solar physics, you need to consider the pickup processes of neutral particles that can actually accelerate. I mean, it can actually give the double of the velocity and can add to the acceleration. I'm just wondering that the pickup process of neutral particles, does it have any or in this simulation?
So could someone maybe repeat the question? Because it was hard to hear from Zoom.
If I understood well, you're asking about the impact of neutral particles on, or like in these simulations. So like here, for instance, that was like just in the immediate surrounding, we were just considering a corona made of electron-positron pairs. But indeed, from the disk, you can also expect, so you can also expect to have like protons. So that's not just about like neutral. But like in this case, the difficulty is like mostly numerical, because when you introduce the protons, you have very different time scales, right? Because it's a very different mass you're dealing with. So they are, well, you could put them like as normal particles, but it's gonna just like add like a huge gap in terms of time scales.
So if you reply, please speak in the microphone, because we don't hear it online at all. You need, like, if you have a discussion, you need both to speak in the mic. Thank you.
Yeah, I think the discussion can be done. Yeah,
I was wondering, I understand there are multi-time scales, but factors of 50 are, you know.
I'm not sure. I think the discussion can be done, yeah, or separately.
So yeah, as you emphasize, indeed, a solution is to put like excessively light protons. So some people will put like protons which are only 100 times heavier than electrons and positrons, such as it limits a bit like, and the impact, for instance, on the tearing instability of these kind of things has been studied. So it definitely has an impact on that's why, for instance, I didn't present the spectrum of the particle in terms of Lorentz factor, because the shape of the spectrum I would get, the slope I would get, couldn't be compared to observation because it would probably be wrong. Yeah.
There is a comment from Andre.
Yeah, Tuale, I wanted to go back to original slide showing this structure of sheet and spine in relatively close to the black holes. We know that at least in microquasars, we know from work, for example, from Poshak, that we have first this acceleration and collimation zone with no radiation, basically, and then the optical emission starts at about 1,000 or more Rg, and then we know that radial emission comes from some millions or tens of millions Rg. So maybe we could somehow try to connect this far-away emission. Maybe this far-away emission is from the spine, Blandford, Znaik, and but with emission closer to the black hole. In many models, emission is quite close to the black hole, but now observationally in the hard state jet, we clearly see that initially we have probably Poynting flux dominated zone, which goes to at least 1000 RG.
So indeed, it makes the comparison quite difficult.
I see Greg has his hand up.
Yeah. Again, this is one of the things that in his slide, and we talked about already, but when we keep on
Greg,
saying
you're
Blandford
breaking up. You'll
Znaik,
have
are
to
we
repeat
really
your
just using
question.
a shorthand for spin extraction? Sorry, I'll turn off my video. Maybe that will help. When we keep on saying Blandford Znaik, are we really just using shorthand for spin extraction from the accretor, or are we talking about really Blandford Znaik? Because as Pop pointed out, you know, we've got jets in objects that aren't black holes. And, you know, I asked that in relationship to Anjay's.
I mean, certainly I would say that the black holes are much more efficient at producing jetted emission, whether it's in the radio, submillimeter, infrared, or even up to the optical band. We haven't seen that strength of jets from the other compact objects, and maybe that is telling us something.
Please.
Well, to answer, Greg, I think what I meant that we see in the hard state jets, we see this ACZ, acceleration inclination zone, with no emission, which has to be then Poynting flux dominated up to large radii. So what I meant by Blandford Znaik, I meant models in which we have strong magnetic fields and large scale magnetic fields that can transfer power to large distances, and whatever its origin.
Another comment here.
So I'm Matteo Lucchini. I just want to make a quick comment on
Please,
the
please
location.
speak in the microphone.
Sorry, I'm Matteo Lucchini. I just want to make a quick comment on the location of where the emission kicks in AGN, especially blazars. When people do these models, which to some extent are even simpler than what we do in X-ray binaries, they still put that first acceleration region at hundreds to thousands of RG. So in that sense, it's not terribly different. What is different is the Lorentz factor of the outflow, but of course, these sources are much more face-on, so maybe we're seeing something different. But in that sense, yeah, it's not completely different. Even some of these spine sheath images of M87, the spatial scales that are picked out are hundreds to thousands of RG. So it's close enough.
So what about emission very close to horizon, like one from M87, yeah?
So if you're referring to the HT image, for instance, I'm not in the HT modeling team, so maybe Sarah can chime in, but from what I remember, about 90% of that was thermal emission from the accretion flow, and only some very relatively low flux, like 10% or so, was from the jet. But that's post-processing GRMHT simulations that are non-radiative, just one fluid. So there may be room to account for that, but maybe Sarah wants to chime in.
Yeah, I didn't quite understand maybe the question, but I think the point is the emission where it's coming from. We don't have for EHT that close to the jet. Unfortunately, there's actually no spectral information. It's a single frequency. So the problem is we don't actually know, it's model dependent, what fraction is thermal and what fraction is non-thermal. And then it comes into like multi-wavelength, but of course you don't have equivalently good resolution in the multi-wavelength. So then it also is model dependent. So I think we don't know exactly the particle properties close to the black hole in M87.
May I have also a comment actually on AGN, if I remember correctly. So VLBI observations suggest high velocity, I mean, for a Lorentz factor of 10 or even more. While when you look at the hotspots in AGNs, you don't need such speed. And actually, the estimated speed is v over, I mean, of the order half of the speed of light, or this type of velocity, suggesting that you have two components again, which was suggested before, or something else that slow down your jets. But I don't know if you have any clue about that, and if it can help to understand the jets in XRB.
So sorry, Pop, I'm not gonna bring an answer, but more an additional question, but kind of related. Also related to what Sarah said in some terms of cooling and emission earlier on. As a theory person, I'm wondering how Rob yesterday on Slack reminded us that most of the power of the jets is kinetic. So how do we, in X-ray binaries and in supermassive black holes, how sure are we of the kinetic jet power based on the radiative power that we see? Do we have like a clear understanding in terms of emission models and cooling of this jet edges?
So to answer that last question, as somebody who does SED jet models, constraining the jet power is horribly difficult because you can always have, let's say, 1 to 2 order of magnitude uncertainty depending on how many pairs you put in there. So the kinetic power is really, really hard to constrain. I don't trust my own jet power estimates at all. Yes, it's 1 or 2, but it's still not great. Regarding the AGN, so the hotspot emission comes from, let's say, tens in FR2 sources, so roughly comparable to these bright hard states, HIMSS states maybe. It comes from hundreds of kiloparsec to megaparsec scale, which in RG is some 10 to the 10, I think. It's bigger than the scales picked out by the radio emission we see in X-ray binaries. So it's not straightforward to draw a comparison, I think.
This actually brings us to 3 minutes past the half hour. Any final comments before we head off to lunch? I think you're all keen for lunch. Thank you to the discussion leaders for this very important discussion session, and all the speakers in the morning, and see you all at 4 o'clock.
Thank you.
Thanks, bye.
Bye.
Okay, bye-bye, guys. See you at 4.
Pan Video, are you there? Is the technician there?
Yeah, Victoria, this is Vicky.
Yeah, do you know whether our technician is still there? He is co-host and can stop the video, because I got kicked out and can't stop the recording.
Are you saying you're missing recording?
No, we are not missing. Is the person who's operating the camera still in?
So what do you want exactly?
I want to ask Nicola to stop the recording because Jerome is off and I got kicked out and I'm not admin and not host anymore.
Yeah, Pierre is going to get the technician.
Thank you so much.
Yeah.